start the webinar today. Hello, of course, to everyone who already joined. Okay, then I would suggest we don't wait too long. So first off, again, welcome to everyone who's joining today's iteration of the FHI-aims webinar series. Again, thank you everyone who's here. Also, thank you one of our speakers, Ray Miyazaki, who's already here and who will also be introduced in a second. So today, the topic of the webinar is heterogeneous catalysis, and also giving the first introductory talk. And I will really focus on the FHI-aims software package to give all of you who might be either new users or who have not heard of FHI-aims before, Ray Miyazaki, who is currently assistant professor at the Institute of Catalysis at the Hokkaido University in Japan. He was also a 2-year postdoc before at the Fritz-Haber Institute here in Berlin, but he will also give a more personal introduction during his talk. So he's just this 1 day planned for this webinar, but we also have a day 2. And here I really want to point out every one of you is welcome to join. So we will have a hands-on and discussion session in the morning Europe time. So that's 9 a.m. CEST, as well as one later on. You can still do so. Otherwise, if you have signed up and registered, you should have already gotten an invitation link to join the tutorial session with some more details on what you have to do to actually log onto the resources and so on. So, but as I mentioned, you still have time to register. So if you want to do so, we have also set up a Slack channel for general questions concerning the FHI-aims webinar. So this invitation, you also want to point, I also want to point out that we have a YouTube channel. So if you go to YouTube and type in MS1PEV, you will also find that we produce smaller YouTube videos. In this case, we also have the basics of FHI-aims tutorial, which gives you a first overview of the input and output structure of the code. But more on FHI-aims in a second. So the topic of the tutorial for tomorrow will be on how to simulate SLES systems for heterogeneous catalysis with FHI-aims. Cobalt nanoparticle on top of an amorphous silica surface. So we'll find out how to model these kinds of systems with FHI-aims. Okay, so then I briefly change my slides here. And then we are ready to start the first talk, which again, I have the pleasure of giving you first talk. And it will be a general introduction to the FHI-aims software package. So to give a brief introduction of myself, so I'm Konstantin Leon. I currently work as a software CV. And you will find out also in a bit what this nonprofit association in Berlin is actually doing. Of work in one research group or by just a few individuals, it's really a collection of people with contributions of over 150 people nowadays from all over the world, from Berlin, Duke, UNC, so the US, China and Beijing, Helsinki, Cardiff, Dalhousie, Warwick, and so on. So it's really a collection of people all over the world. But FHI-aims as a code has some what we call the aims coordinators. So these are Volker Blum, history of code development. So nowadays it's more than 20 years of development. And these 150 people really has to be pointed out in more detail. So this is from our website at FHI-aims.org, where you can find the full collection of people that contributed to the code that we'll showcase here today. And to again summarize a bit what the FHI-aims code is, it's really community-based. That means it's really an open development platform. So if you're a research group, whether in industry or in academia, and you're interested in developing do your independent developments. So, and these new physics and developments are constantly being added, really by scientific groups around the world, without really to do so. Now, I already talked a bit about MS1P. So MS1P, Molecular Simulations from First Principles, is a German nonprofit. We try to help with code stability and integration. So if there are issues with integrating new features into the code or just stabilizing the code in general, we'll try to help out. We are also here for community support. So we manage, for example, the community channels for FHI-aims, which is the Slack channel, as well as the development GitLab channels. And we're working on documentation, webinars such as this one, online tutorials, and we're really trying to help the community as a whole that surrounds FHI-aims. And MS1P and its structure has an executive board. That's really a brief overview of what FHI-aims and MS1P are, in case you were interested maybe what the distinction is between the two. Then let's go to the actual design principles behind what makes FHI-aims what it is. So from the onset, there was a vision that FHI-aims should these without a priori precision and accuracy limitations. And that was really something that had to be, was decided from the onset. All electron code, it should be able to handle non-periodic and periodic systems on equal footing. So whether you have periodic boundary conditions or not, it should scale to extremely large systems. So that can mean thousands of atoms, or as you will see later on, even 10,000s of atoms without limitations. It should scale both on laptops as well as massively parallel HPC architectures. And in the end, this is also supported within the code. And the key design choice behind FHI-aims is really what kind of basis. So let's dive right in. Let's say talk a bit more about these atom-centered orbitals. So expansion, and then you have here an expansion in terms of basis functions phi-i. And these phi-i, you are free to choose what kind of basis functions you want to use. As mentioned, FHI-aims decided on numeric atom-centered orbitals, which are shown here on the right side. And you have a part, this was chosen, and you can see the structure here of the radial function down below, as that this is not an analytical function, but rather a numerically tabulated one. So you are quite flexible in what kind of choice of basis functions you want to have. And there's also a possibility to define, for example, here a cutoff potential to really set an exact zero at some type of radius. And what this gives you, let's say in a nutshell, is one, you have this extremely flexible shape. All these have an all-electron description. So within FHI-aims, there's no let's say, a distinction between what are core electrons and have O of n computational scaling for the most expensive steps. And that's, of course, really important for us to gain good scalability to larger system size. And in the end, because you also have, for example, here this cutoff potential, you actually need a rather compact basis set if you want to get more or less converged results with respect to here total energies in most systems. Then the important thing is you are quite flexible, but you still have to decide on what kind of basis functions you want to use for all the elements. And so for this, there are within FHI-aims, you already have a basis set library available on converged results with respect to DFT calculations and total energy. We also have basis sets that go beyond just simple DFT. So for example, we hope with this, or we think that this really makes it also easier for new users to start right away because they don't have to handle all of the specific basis set setup, but you always have the flexibility to change things yourself. So that's really one of the main key parts of the code. FHI-aims for DFT calculations has already been also shown in literature. So this is, some of you might know this is the delta test, which was published in 2016. And the main part here, the 15 codes were compared between all electron and pseudopotential codes. And here actually the FHI-aims results, which you see in the second row, on par with all the other all electron code based implementations here. So this is really, of course, one of the main pillars we want to focus on. So we want to be precise, we want to be accurate, but we also want to be efficient. So this is here the reference again for the delta test, GPU acceleration, to also allow these efficient computations on newer architectures. We have, for example, also a band structure benchmark with spin orbit coupling, if this is what you're interested in, as well as, for example, here. Then I wanted to point out one specific, really more or less recent advancement in our eyes, which is hybrid density functional theory. So, which with more or less optimal scaling, but the same for hybrid GFT required a lot of work. And here I want to point out this is really work over more than a decade. So this really has to be, let's say, stressed that this is a lot of work by all the people involved. But we're really happy that this is in the code now. So what you see here are some benchmarks for gallium arsenide supercells with the hybrid function HC, the new implementation. And you will see also in a second actual systems, which may be more of interest than just gallium arsenide. We were able to, or the researchers, including Sebastian Kokot and others, as you will see. As you can see, the end of the x-axis here is nearly 10,000 cores that were run on an MPCDF, so dealing with the respect to the number of atoms. So not just with the number of MPIs tasked, but also with the number of atoms, we almost achieve ideal OFN scaling. And why this is now, of course, very exciting is that you can go to much larger systems than what probably a lot have thought. So you can really see it's hybrid perovskites, it's paracetamol supercell, and then you see on the right side, both of these plots are larger ice supercells. So the largest cell that was simulated is an ice supercell with over 30, quite amazing. And you can see that at this kind of system size, the bottleneck is really what we call here ELPA. So that's the eigenvalue solution. So ELPA here is an external library to solve the eigenvalue problem. Something we'll see also later on when I will talk a bit more about the FHI-aims ecosystem. A host of features, of course, which are implemented in conjunction with these hybrid density functionals. And this is an excerpt of the roadmap, which is published as a preprint, maybe already before Easter. So yeah, maybe you're lucky enough, and this is an Easter present, whether it's a D3 correction, many-body dispersion, or XDM, and all kinds of output functionality as well. And what we've already seen in recent times, so these are two recent papers, is that this now really allows other researchers to also create, mostly based on GGA or GGA plus U level calculations. But we think now that with FHI-aims, this really allows also to do extremely high 0 plus MBD to calculate the total energies as well as other properties. So MBD here is the many-body FHI-aims DFT calculations in the database. And they trained this on molecules ranging with elements all over the periodic table. So the hope, and we have to see if that's actually achievable, and other researchers would try those, of course, to have a foundation model based on hybrid level. The Google DeepMind team, also in the group of Klaus-Robert Müller. And the second paper here is also from Klaus-Robert Müller, as well as Alexander, to train already a neural network force field. So I think that's already quite exciting development in this direction. So that's FHI-aims and some more focus on the hybrid functionals. But FHI-aims as a whole is, of course, a large ecosystem. So you have the main FHI-aims package, which really does the electronic structure-based part. But FHI-aims is really based on several external libraries, which are open source and which I think is critical for any kind of electronic structure code. And that includes, for one else, two different eigenvalue solvers and just general things that are needed for electronic structure calculations. We also have support for several exchange correlation functionals via libxc, as well as the dispersion corrections via libmbd. And then even going beyond, in this case, general, also has support for external workflow drivers. So that's here, for example, IPy, the ASE Python package, Python, FHI vibes, and so on, and many more. As well as tutorial tomorrow is something you will also then see there. And I just wanted to briefly mention FHI-aims can also be used as a library. So we have, for example, the Hamiltonian and stuff. This is also possible. We have additional Klim's Python package, which is a collection of command line tools, well, like Automate2, AIDA, Task Blaster, and so on. And then lastly, something we've worked on relatively recently is FHI-aims. So that's really a dedicated FHI-aims IO library, which we hope will make development much easier for the future, also for new developers. Okay, some more information, maybe trying out the code and so on. And there I would really suggest to go to our website. So that's FHI-aims.org. Interested, how do we get the code? Keep in mind for academic groups, it's only for a voluntary license fee. So if you're just interested in contributing and so on, you can freely do so. Just go to the website to see. And then one other thing I want to point out, which I think is very important, contributed by external people. So again, I want to point out the big work that has come here from the community. And this tutorials page is really already quite extensive and it just keeps on growing. And we're really happy that it does. And it goes from all kinds of topics, from fundamentals of FHI, molecular dynamics, complex workflow, spectroscopy, and so on and so forth. So this, I think, is a really good, I already mentioned. And if you're interested, please feel free to join there. And then the last thing I want to point out is, again, our YouTube channel on different tutorials that we had in the past, like the fusion barriers, how to calculate thermal transport, how to do these kinds of dispersion-corrected hybrid DFT calculations. So if you're interested, please also go to the YouTube channel, check them out, give us feedback, of course, if you would like to see something specific. Briefly, so FHI-aims is really an electronic structure code based on numeric atom-centered orbitals. And with this, I think we really in liquids all on the same footing. I think we've shown that we can be very precise and accurate. We can do large-scale hybrid DFT, including dispersion corrections, but also go to many-body methods. And we are scalable even on small machines like laptops, but up to 10,000, of course, on HPC systems. So with this is it for the introduction. I want to thank you all again. And yeah, the session is open for questions from your side now. Thank you. Of the webinar. So if you have questions, there's a Q&A button which you can click and then just ask your questions and we'll go through this. Yeah, and the actual Q&A will be led by one of my colleagues, which is Andrei Sobolev, and I think he can just introduce himself now. Thank you. Of course, if in case you don't want to.
Okay. There is a question by Ahmed Mahmoudov. The question is, how well the code scales on multiple GPUs for the calculations involving hybrid functionals?
Yeah, that's a good question. So it is being worked on. It is one of the topics that we want to address also for the future. So we hope that these scaling improvements can also be there for the hybrid functions. So at the moment, I think it's the speed up is not drastically there for the hybrid functionals, mostly because we would have to optimize the exact GPUs for hybrids. I don't know the exact benchmarks at the moment, but yeah, I would just say it's active work. I don't know exactly the performance there.
Can FHI-aims be integrated with crystal structure prediction methods?
Yes, thank you, Ashok. So yes, this was actually done by one of the, let's say, main providers for crystal structure prediction in industry. And they really have shown that PBE0 calculations for FHI-aims, including dispersion corrections, are really are one of the ways to go working with FHI-aims. So I would say absolutely it can be integrated with crystal structure prediction methods. Specifically, the hybrid functional implementation is their key.
Thanks a lot. From the anonymous attendee, technical question. You said the radial basis functions are not analytical but tabulated. I thought they were hydrogenic functions generated by solving the H-atom Schrödinger equation with some modifications, additional potentials.
I don't know if I can refer here to Volker, who was really the main developer and who knows best about these basis functions. So maybe he can give a better answer than me there.
Yes, so you can toggle this behavior. So if you want the hydrogen-like functions with performance, and that is done numerically, but you can toggle a switch and then you can get analytical hydrogen-like functions with an exponential tail, but they work.
Thank you, Volker. I hope that answers the question. If you have, of course.
If it is only hydrogen type of functions, in principle, actually, it's not only. I mean, you can do hydrogen functions, but what we typically do, we solve really the numerical Schrödinger equation for a free atom, right, with a cutoff potential, so that the wave functions do not range too long. But
yes, yes, for the minimal basis and for the atomic-like functions, that's of course true. And there are more basis function types. I guess this, and we do, and Slater type orbitals can do the same thing.
Energies of systems from the output files for calculations performed using FHI-aims with DFT methods.
So I'm guessing you're interested in the actual basis function form and on what you get out and so on. I think, yes, you can extract those from within the code as basis functions. But I don't know, Volker, if you have on the top of your head what's mentioned in the manual there.
Specifically, what is the radial density? So of course you can actually print the decomposition of the full density of an extended system. Not 100% sure how to interpret that without a better definition, but maybe I'm just slow, which could be. But all these things can be printed if we know about them and given time, right? Often we don't know the use case, and once we know, that's actually for the other question. That's a very interesting builder. I don't think it has a heterostructure building tool yet as a matter of being integrated there, but I think the underlying ASE
Q&A functional introduction again to who he is and what kind of work he's doing. So Ray, I will stop sharing and then you can start sharing your slides.
Yes. I hope it is
yes,
fine now.
We see it now.
My talk now?
Yes, you are ready. So I can see
Okay.
everything should work.
Yeah. So hello everyone, I'm Ray Miyazaki from a FHI-aims tutorial. So then I'd like to thank for Konstantin and the other people of the MS1P and the FHI. So today I'd like to talk about the density functional theory approaches for modeling heterogeneous catalysis. So before entering my talk, I would like to university. So actually, I got a PhD in the same laboratory with Professor Junya Hasegawa. So and then I did a 1-year postdoc, and then from 2021 I moved to the Fritz Haber Institute of the Max Planck Society as a postdoc, and then become an assistant professor. So now I belong to the Hasegawa group. So now we have the 10 members. Actually, it is relatively small group, but I believe a brief introduction of our institute. So here, this is a map of the Japan, and here's the Tokyo and the Kyoto in the main island. But our institute located in here, Sapporo City, so located in the northern island of Japan. So the institute is relatively small, but they have the long history. Actually, our institute was established in 1943, and this is the oldest. So, and because our institute located in the northern part, in the winter, we have a lot of snows. Actually, I took those photos by myself in our university in midwinter. And nowadays, of course, the amount of we will have a nice spring season. Then I say Hokkaido is a very nice place and our institute is very nice. So first, I would like to talk about my scientific interest. So this is a very typical equation of the chemical reaction here. How to say the product of the C or ratio of the C. And this reaction connected by this arrow. But point is, in the textbook, there's a very limited description about the mechanism behind of this arrow calculation and recently AI. So for example, by using ab initio calculations with like a DFT, we can get this kind of reaction pathways of the catalytic reactions. And then from this, we can extract some kind of catalytic mechanisms, intelligence, and then we can get some kind of descriptive parameters that correlate with the target catalytic performance. And then by using those approaches, we can get the design, the main research topics recent days. And the target is heterogeneous catalyst. And most of you already know the heterogeneous catalyst is very essential and important technology or materials for the molecule. And that means there's a lot of factors that affect the catalytic activity. Here, this is a very typical picture of the heterogeneous catalyst. Here is a metal nanoparticle supported on the support material. And for example, here, of course, metal surface is the active site, but also interfacial site between the metal and the support material is a very important active site also. And this metal nanoparticle itself also has a very complicated structure, like several facets and several active sites. Then the mechanism of catalytic reaction that proceed in the atomic scale is hard to be elucidated only by experimental approaches. Then we can get atomic scale reaction pathways and effect of electric state of the catalyst to the mechanism. Then it is very nice approaches, but problem is due to this complexity, it is very hard to explicitly include all of the structures and factors of the catalyst to the atomistic model with ab initio calculations. Then we need to extract the factors that essentially contribute to the catalysis that enable us to the elucidating because by using both sides of the narratives from theory and experiment, we can propose the design criteria for the new catalyst from both sides. So this is a very general introduction of the application of my DFT calculations for this CO2 hydrogenation by cobalt catalyst, and most of the results are published in those two papers. So, and in this project, I focused the silica support. And in this kind of catalyst, not only this metal nanoparticle, but also the support material and the interaction with them are very important for the catalytic performance. Then they're not fully established yet. Then in this study, we particularly focus on the role of the modified silica support for the CO2 hydrogenation by using this catalyst. And this catalytic, the hydrothermal vent environment by using this catalytic system, hydrothermal vent is the fissure on the seafloor, and then discharging some operators investigated how first organic molecules are generated at the hydrothermal. Of course, all of the calculation performed with the FHI-aims, and even though the version of the FHI-aims is a little bit older, but it was. And because the ground state of the cobalt is a ferromagnetic state, then I adapted the spin collinear calculation basis set. Then by using the optimized structure, I performed a single point calculation with title basis set to get a reliable or more. we would like to perform some kind of DFT calculation for this catalytic system, but then we need to build the theoretical model. For example, for this metal cobalt nanoparticle, the experimental particle size of the cobalt is about 8 nanometer metal nanoparticle. And for support material, the support material has the amorphous structure. Then one question is how to model this kind of non-crystal is there are incorporated metals into the silica, but how to incorporate those additive metals structure is what is the structure. Detailed structure like shape or morphology is unknown for this kind of heterogeneous catalyst. Then explicit atoms that would correlate with the performance. For example, first this cobalt nanoparticle part, but this is a very, how to say, practical size for simulation. But fortunately, there's one previous study. Based on that study, from around the cobalt 55 size, the adsorption energy of the small molecules is almost constant against the size of the small molecule. Then the result with cobalt 20 model can be compared with those of the cobalt 55, then if the reliable model for the simulation. And for silica, this is also fortunately the Comas Bibbs. And then in this study, they performed the molecular dynamics simulation with high temperature and then making non-crystalline structure and then gradually cooling down the simulation. I picked up this model from this literature and then performed the geometry optimization with our computational setting, the silica surface and the cobalt cluster. But next question is how to put this cobalt 20 cluster onto the amorphous silica surface. We can freely put the cobalt cluster onto it. Then based on this previous study, this kind of metal nanoparticle contact with the metal nanoparticle directly bonded with the silica via oxygen atom. Then, as you can see here in the I groups, then I put the cobalt 20 cluster model right above each OH group, and then removing the hydrogen atom point and comparing the relative stability of them. And this is the result, and that means the negative energy with this energy, this equation got the most stable one. This one, number 23, and this structure shows the minus 2.24 electron volt for formation. The model is contact with the silica with 5 OH group without hydrogen catalyst. And then what we can do? So first, we can, of course, investigate the electronic structure. Here, I investigate them. In FHI-aims, you can use this kind of keyword in control.a file. And here, I show the result of the Hirschfeld charge analysis, and then I picked up the top 3 negatively charged cobalt atoms and the top 3 positive charged. But the negatively or neutrally charged cobalt is located as the top layer of cobalt due to the interaction with the silica support. Then we can get such kind of electronic structure information from those that is CO2 hydrogenation. Then we are interested in the interaction with molecules and the catalyst. And here I investigated so here this is the energy of the total model, and the isolated energy of the isolated model is subtracted. And here because as you can see here, there's a lot of adsorption sites of the cobalt cluster. Then the question is how to negatively charge the site and most positively charge the site of the cobalt cluster. Because as I showed before, here this is a CO2 adsorption structure as the most negatively charged, or that means metallic cobalt site. And actually, current adsorption energy calculated to be the minus 0.27 electron volt. That means the CO2 prefer to be adsorbed at the metallic cobalt site here, and then adsorption site. And as I mentioned, cobalt 20 cluster is too small for actual 5 SiO2 model with this cobalt 55 cluster. And I put the CO2 as the most negative side and the most positive side again for cobalt 55. And as you can see here, the CO2 adsorption energy for same with the cobalt 20 cluster model. Then the adsorption trend of CO2 is qualitatively, not quantitatively, but qualitatively represented by cobalt-28 cluster model, then that model has some kind of reliability for the simulation of the small molecular interaction with cobalt nanoparticle to the amorphous silica. And then the remaining question is how to incorporate the additive metal to represent the difference of the support material, unknown. Then we need to focus on the specific point of the catalyst. Now to focus on the additive metals in the stable oxidation state at the interface site. So this is what I mean. So actually I incorporated those additive metals with keeping the stable oxidation state or oxidation state. Then I simply replace the silicon atom by titanium or zirconium. Then, this 4+ oxidation state. But for aluminum prefer to be a 3+ state. Then system to be neutral, then we need to put the 1 proton as the, oxygen atom as the interface site. And for finally, calcium and magnesium, those metals prefer to be 2+ state. Then I put those metals at the bridge site, normally 2+ oxidation state. Then, of course, there's a lot of possibility for the actual or operanto structure of the additive metals into the silica support, but I put the one, where should we incorporate the additive metals onto the silica support. And again, then at the interface site, then I simply replace those silicon atoms by titanium and zirconium, and then compare the stability. Here, this is a result. And actually, I replaced the A, B, C, D silicon by titanium and zirconium, and then calculated, decide where should we put these additive metals onto the silica. And yes, and effect of the difference of the support material. For example, this is a result of the CO2 adsorption at the interface site of each model, titanium, zirconium, aluminum. CO2 at the interface site extend to the reaction mechanism investigation. For example, we can calculate the transition state, connecting each intermediate, what I showed before. And then finally, we can get the energy diagram here. This is a y-axis represents the energy, and the x-axis represents the reaction coordinate. And then we can get the reaction pathways. And by comparing those pathways, we can get main reaction pathway towards the target product. And this kind of calculation can be achieved by using naturally elastic band calculations with atomic simulation environment and FHI-aims. And or you can get some more detailed electron structure analysis here. Even though this is a different charge transfer from support material to the supported gold cluster, and you can get some reason or mechanism for the high activity of the catalyst, design criteria for new catalyst. And even though, actually, those kind of investigation was not performed with the cobalt catalyst, but those calculations actually performed in this paper. Then if you were interested in, please check this paper. And this is actually my approaches for heterogeneous catalysis with DFT. And actually, chemical reactions at surface is very powerful for DFT, but actual, heterogeneous catalysis is interplay between the multi-scale processes. For example, transportation of the reactant product gases at the experimental reactor. This is a macro scale, or reconstruction of the catalyst. Then we need to focus or extract the important part of the catalyst. And as I showed, by using the DFT calculations, we can access the underlying mechanism of the catalyst, and those insights can be combined with AI. And the more details are summarized in those papers. And finally, I'd like to thank for my collaborators, and the Professor Matthias Schäfer and the Dr. Lukas Hopper at the Fritz Haber Institute and the Nomad Group. And the experimental collaborator is Harun and Kendra at the Max Planck Institute for core reinforcement. And I would also thank for the funding from the Big Max and the FunCat project. And thank you very much for your kind attention.
Thank you, Ray. Very nice talk. Thank you for staying on time. So this was all perfect. So I think we can continue with the Q&A part. So I will hand over again to Andre to handle the questions. Feel free again, write in the Q&A chat box. You can also write.
So if you have any questions, please feel free to write. Okay, we'll give some time to type in the questions, or you can raise your hand and we can let you speak if that's more convenient to you. Okay, there is one question from Ashok Kumar. For such complex heterogeneous catalysis calculations?
Actually, is it better to answer by myself? He would like to talk about the machine learning potential like implemented in BASP, like.
Well, in parts, that's because FHI-aims is actually efficient with the all-electron implementation. I think that's a relatively frequent method that does not need to change the underlying potential with various problems that could arise. Now, that being said, so is on the list that we've sort of formulated for ourselves to add on one of the slides, one of these methods, and that's definitely something where they've been used for a long time in FHI-aims. We do have a frozen core approach implemented in FHI-aims that also reduces the computational effort, especially
because I mean, Ray already said it could be that the question was a little bit misspelled, because on the fly sounds a little bit like machine learned potentials. So what we have already, but not public, but it will be public in a month or so, including really machine learned potentials. And I should also say, maybe later Konstantin will say that anyhow, we will have agents including CISO and machine learned potentials and deep H. So that exists part of the GIMS, of the graphical user interface.
Thanks a lot.
Sounds very exciting.
Yeah. Did you use to select the orientation of the nanoparticle to be absorbed on a substrate?
I know the metal cluster is interaction between the metal cluster and the support material is stabilized by interaction with the oxygen cluster and the support material. And then I picked up the most planar and the most large facet site. I hope this is the answer for this.
Thanks a lot. There is one more question from anonymous attendee. How do you consider the magnetic behavior before making a slab?
Actually, I picked up the this cobalt cluster structure from the previous report, and actually that previous report actually even for the bulk cobalt, the ground state is a ferromagnetic state. Then optimization, and then after the SCF calculation and geometry optimization, of course, the optimized electron structure is slightly deviate from the original triplet state, but keep the ferromagnetic state, and it is actually stable than the singlet state. And in this case, in experiments, the anti-ferromagnetic structure is reported as the most stable one. And then I put actually after the SCF, we can get the stable anti-ferromagnetic structure. Then you are right. Actually, before performing the calculation, we need to know.
Thanks a lot. Hope this answers the question. Yeah, there is one more question from Oscar van Vuren. Have you considered the possibility of cationic defect species from the silica migrating into the cobalt nanoparticle?
The collaborator mentions that particularly for titanium case, they investigate these kind of those species are randomly dispersed at the but they also found the kind of island structure of the titanium oxide at the interface. That means as you know, the titanium oxide probably making some contribute to the high catalytic activity, I think. But as I mentioned, it is unknown things for me because I like to make some data for AI, and then this kind of special data for titanium is not so have not carefully focused on this part, but in particular at the operant situation, probably this kind of we need more how to carefully modeling this, and also experimental based on the experimental better ratio at the surface. We need to put at least 10 titanium in my talk. Then this is a approximated model for the catalytic system. But if you are interested in the
Thanks a lot. There is a next question from Zhaoqing Liu from superposition error in FHI-aims for catalysis, particularly for absorption energy.
Yeah, good question. The FHI-aims, right?
I can comment.
Yes.
So I think this is a frequent question from the quantum chemistry community, but it's all a BSSE correction practice. So this is already addressed in the first FHI-aims paper in 2009, and that experience near the nucleus and our NAO basis functions near the nucleus actually are very good and very precise. So the BSSE we have not even close to primarily BSSE. In fact, if you want to increase the basis set, you may improve other things up to this typically. And for correlated methods, this is different because you have a sum over unoccupied states, and there we can do a BSSE correction. And I think that's what Ray is also referring to, that there's a recent discussion about BSSE correction and how to do that for periodic systems in the right way for a random.
I hope this answered the question. There are several more questions. So one question is from anonymous attendee.
So actually, first of all, when I performing this calculation with FHI-aims, there's no implementation for charge analysis implemented in FHI-aims. But after that, formation generating the electric density for beta charge analysis was nicely improved. Important point is there's no golden standard for charge analysis because that is very artificial. Electron is moving around. Then my opinion is okay, even with hash rate analysis or beta charge analysis, we need to be checked just raw data of the electron structure. And then this is just a difference between the interacted system and the isolated system. And then here, as you can see here, yellow region is the electron accumulation region, and the photomaterial to cluster is nicely represented. And also in this system, I performed also a hash rate charge analysis, and the hash rate charge analysis also shows the charge accumulation at the cobalt with each other. That means the charge density, population analysis is very nicely worked for this system. Probably can charge analysis, but the important point is we need, in my opinion, we need to check the electric structure with different aspects, like those.
It's not great. And there are two more questions by Masood.
I completely forgot about the mentioning about the thank for the previous study. And actually, in those two studies, they are investigated the stable structure of each size of the cobalt cluster by using investigated the several size of the cobalt cluster, and then actually I picked up the cobalt 20 cluster because this is a global optimization. But thanks for this previous studies, I can pick up the stable cobalt cluster in the gas phase. Of course, I don't know stable cluster at the gas phase as the initial structure for geometry of the optimization.
Thank you. One more question from anonymous attendee.
Yeah, right. So actually, in this calculation, I just use the simple RPBE without any van der Waals correction. For this, I adopted Takechenko-Sheffler type van der Waals correction experimental report for the adsorption energy and the vibrational frequency of the CO on the surface. And then I realized that, as other people mentioned, van der Waals interaction is very nicely for represents the adsorption van der Waals correction for chemi-solved structure. Actually, adsorption energy of the small molecule is largely overestimated. Actually, largely, how to say, did not use the van der Waals correction for this calculation. And of course, I also investigated the crystal, lattice constant of the bulk cobalt with RPB, and then those are also nicely represented by bare RPB. Then I decided not to use the van der Waals correction for this.
Find in general is that the Tkachenko-Scheffler, which was the very first development, right, is somewhat overestimating van der Waals corrections. And if you come to short distances, PBE in fact has some van der Waals included of the dispersion to have a more realistic thing. But again, for short distances, if you really look at chemisorption, that is not so important for these systems. For other systems, if you will, Scheffler is giving you an idea, but I would say you should really go to the next generation.
Okay, thank you very much.
I guess Dr. Tsutagema asks, are the energies in your results compared?
Actually, that's a very difficult question, I would say. Ideally, we should compare the our difficult to get a reliable experimental result that can be compared with the DFT data. Even for adsorption energies, it is very difficult to get them, and they are difficult. But I would say, actually, as I mentioned in the previous Q&A session, I found some kind of experimental data for carbon monoxide adsorption of the cobalt surface. This is the, how to say, surface science. Maybe it's not so bad selection for this simulation, I would say.
Okay. Thank you, Ray, again.
Thank you very much.
As Andre said, we're a bit low on time now. I think that also thank our panelists for answering questions and helping. And of course, all the attended to point out again the plan for tomorrow. So if you're interested in, we have the hands-on and discussion sessions in the morning Europe time, so 9 a.m. CEST, as well as 3:30 p.m. CEST, where we will run through some of the examples and as well as, for example, here on the right side, the cobalt cluster adsorbed on the silica support. So if you're interested, please come. You can, of course, ask more questions tomorrow. And I hope to see a lot of you there. You still have time to sign up. And I would then close today's webinar. Again, thank you, Ray. Thank you, all the panelists, as well as everyone who was here. I think it was a very nice webinar, as either at the end of this week or early next week. So keep an eye out. We'll try and send it around on our social channels, also in person in Shanghai in November. Otherwise, always remember that we also post our upcoming webinars on our channels. We have new ones planned, which we'll announce shortly. So please keep an eye out for more webinars of this sort. And again, I hope every one of you enjoyed being here. See you all next time. Bye-bye.
Thank you very much.